In this video, we're going to be talking about robot prototyping and the sorts of equipment that are available to you in our labs to allow you to prototype your robots. One thing that we should keep in mind as we go along here is IP, ingress protection ratings. And these allow us to specify, and you'll see them in a whole lot of products, IP67, IP65, IP42, that specify the protection against ingress. The first number is of solid materials, so dust and particles and things like that, and protection against liquids, so waters, for example. So I've developed things, for example, that have been IP67. So they're immersed underwater and they're essentially waterproof and operate in a waterproof environment. I've used them in sewers, for example. I've also produced things that have been a whole lot less waterproof because the requirements have been a whole lot less stringent on them. For example, something in the order of IP43 or IP42. They have protection against a bit of a spray of water, but as soon as you start dunking them in water or anything like that, they're going to fail. Now, clearly, as we head further down the rankings, they're going to be more expensive and more stringent requirements required to actually produce and cater for these protection ratings. Now, my suggestion would be, once we've created all our requirements analysis and our work breakdown structure and things like that, there's a few things that we'll need to do. And creating small scale and test models is actually really handy in this design phase to make sure and verify that particular components are going to work before you scale them up to full size. Also simulations, creating computer simulations or mathematical models of how things will work, how it will work, at what point it will break, and doing CAD models and things can allow us to work out what it will break and where the tension and things is going to be on various parts. Then we'll fabricate them and actually verify them. Do they actually meet the models? Will it break? And how well will it work? Rather than working in the reverse design methodology of just trying to fabricate everything and testing it, let's do a bit of simulation beforehand. But let's actually test it when we fabricate it. At some point, I'm expecting you'll need to develop some software, and that can be something like in LabVIEW or MATLAB. You can use OpenCV for computer vision sort of applications. You can interface things with Arduinos and things, or Raspberry Pis. It doesn't really matter what, as long as you're actually writing some software to control your robot and making it do something. We have downstairs in PS2105 what we call the Modern Manufacturing or Rapid Prototyping Lab. This has got a whole lot of equipment there that I'll briefly go through to give you a bit of an overview of the capabilities that we have that you can use for building a robot. So we've got laser cutter, wordjet cutter, milling machines, several printers, 3D printers, FDM ones, fused deposition modeling, and SLA ones, and a carbon fiber one as well. So we'll go through what these actually do and how they work. Firstly, the laser cutter uses a CO2 laser to cut through materials, and we can cut through up to about an inch of acrylic or perspex. So we've got a sheet of material and we perform 2D cutting on this. The typical thicknesses we use are about 3mm or 6mm, and we can do perspex and acrylic. We can also do wood, paper, leather, cardboard, things like that. And we can cut sheets up to 600 by 900 millimeters in size. Next we have wordjet cutting. So here we have a high pressure wordjet up to about 45,000 psi mixed with garnet to cut through material. And here it's once again 2D cutting, and we can cut virtually anything. All metals, stainless steel, steel, aluminium. We can do glass, rubber, foam, plastic, stone, tiles, pretty well anything. They produce all the stone bench tops for people's kitchens on these sort of things. About the only thing that we can't cut is tempered glass, because that will crack as soon as you pierce it. You can't actually cut it. Or we can't cut things that will be completely destroyed when we immerse them in water. Now here we can cut to 1.5 meters by 1.5 meters, and 30mm thicknesses are very easy to do. We can actually do more than that as well. And then we have milling machines. So we've got a few milling machines. We've got carbide or high-speed steel milling heads on them. They quickly cut away or drill materials. And here we'll typically work with metal, so aluminiums and steels and things like that. We can also work with things like Delrin or wood. And here we've got fab dimensions that are a fair bit smaller, but we can work more easily in 3 dimensions. We're not just cutting out of a sheet like we were with laser cutting or with our wordjet cutting. We've got a block that we can mill something out of, and there's a few examples there of things being milled out of. Then we have 3D printing. If our designs don't need to be quite as strong, we can use FDM 3D printing, where we heat plastic to about 200 degrees Celsius and extrude it out and build it up layer by laying down some plastic. And typically we're using ABS or PLA plastic. Now we've got a number of different printers, and we've got the WIT boxes, which are the standard ones that are in most of the labs, and we've got some Wanhao ones that go significantly higher and give us a much larger printing volume, about 3 times the printing volume. We also have an SLA printer. This SLA printer we use for doing very intricate work. The step resolution on this is much smaller, and we can do very fine details that we can't do with our FDM 3D printers. Then we have a carbon fiber printer as well, and the carbon fiber printer lays down a carbon fiber filament internally within our 3D prints to make it much stronger. The manufacturers talk about this carbon fiber, and we can use Kevlar and other exotic materials as well, producing parts about as strong as aluminium but significantly lighter. So carbon fiber printer that's available to us as well. We also have a whole lot of general purpose electrical prototyping equipment as well. So in-house we can do double-sided PCBs. They're not plated through hole though. We can do external ones as well. We've got a whole lot of test equipment like digital storage oscilloscopes, function generators, multimeters. I'd suggest that at some point you'll be using breadboards and development boards to create your designs before you actually create them on a PCB, and this allows you to prototype them and ensure they work before you actually get to your final product. In terms of producing structural elements as well, probably the quickest way to produce some structural frames is use some of this aluminium extrusion. It comes in a few different sizes, like 30-30, that's 30 mil by 30 mil, or 40-40, 40 mil by 40 mil, and they've got these nice grooves in them. Now we've got these up to 2 meters in length, and you use T-bolts to, the T-bolt goes into this groove, and then as you tighten it up, it turns around and locks against the groove. They're very strong and have many mounting points. You can kind of mount anywhere along that particular groove, and they're reconfigurable, so you just unscrew them and change it to a different point. And you can easily bolt aluminium to these, acrylic to these, whatever you want, and you just use the T-bolts and or the T-nuts and some little bolts. They're about $16 a meter, so not particularly expensive either, and we can cut them to particular lengths using a cold cut saw and get very precise measurements using that.